Well, howdy, folks. How are we all doing today? So for our next lesson in chapter 1, we get to something called inverse functions. So real briefly, let's just spend a quick second reviewing what an inverse function is. So let me see if I can draw a quick little XY axis here. Let's go like that. We said back in integrated 2 and 3 that an inverse function is any function that is reflected over the line y equals x. That's my dashed line there. Not very good, I get that, but it's going to have to do. All right, so this is the line y equals x. So let's get our first graph out here. Let me throw one on here for y'all. Say I got a graph that looks like that. We'll give ourselves a nice little cubic going on here. And just for the fun of it, we'll have it come up like this and then go like that. We'll call this graph f of x. So the inverse graph, an inverse again, that's where we take our x's and y's and flip-flop them. So that means every x coordinate becomes a y coordinate, and every y coordinate becomes an x coordinate. So the inverse relation would be reflected over this line y equals x. So instead of going diagonally down, it would have gone diagonally up. Let's see if I can do this here. Diagonally up this way. And then we have a heel that goes up, so this heel is going to come back through here. And then this was a little bit under the x-axis, so we're going to go a little bit under the y-axis. And if I drew that correctly, if we were somehow able to fold the graph along this dashed line, we'd find out that the blue line and the green line, they would lie on top of each other. So f of x was our original function. The inverse of that would be f prime of x. Now, just for the sake of argument, notice this would, our green function, f of x, that would have passed the vertical line test. So we'd say that's a function. But the green function, or the blue function, that inverse function, it would not have passed the vertical line test. Notice right here, on just look at the y-axis. Notice how it crosses the blue graph 3 times. So that means the inverse relationship wouldn't have actually been a function. Still, the inverse is just not a function. So in order to prove that something is a function, we use the vertical line test. But to prove if the inverse will also be a function, we have to use the horizontal line test. So if you look at this parabola right here, it passes the vertical line test. It's a function. But notice, the horizontal line test would not have passed the horizontal line test. Therefore, its inverse is not going to be a function. In other words, say I graph the line y equals x. So I'm going up here like that. There's our line y equals x. If I graph that line y equals x again, so you can kind of see the function. All right, see how it gets reflected over that line y equals x. But notice, while this is a function, the inverse relationship would not have been a function. Okay, so when we're dealing with, in pre-cal, when we're dealing with inverses, we only will deal with just a portion of the inverses that will allow it to also allow the inverse be a function. So for instance, if I were to take a look at this graph here, what if I limit it? And this is called limiting the domain. What if I limit it in such a way that although I know this passes the vertical line test, what if I only took part of the function that would pass also the horizontal line test? In other words, what if I were to have stopped it right here at the line at the point 0, 0? And so that, in other words, the only part I would have taken then would have been this part of the graph, just that little curve. So now it would have passed the vertical line test still, but it also would have passed a horizontal line test. And if by limiting the domain, by restricting it, what ends up happening is when I reflect whatever I limit it to, now my inverse relationship also would have been a function. So although this is a function, I limit the domain so that way when I do the inverse, it's also a function. So in other words, I would have gone over here and while I would have said I want to deal with f of x equals x squared, I would have done one more thing. I would have added a little parenthesis here and I would have added such that x is greater than or equal to 0. So I'm only going to be dealing with the function from x is greater than or equal to 0. Therefore, my inverse function will also end up being a function. So we're going to be talking about functions today, but you're going to see something about limiting the domain. And limiting the domain is not something we dealt with in integrated 2 and 3, but we are going to do it a little bit here now. In other words, we don't, and again, another way to restate it, we're just not using the entire function. We're only using as much of the function as we can so that it passes the vertical line test and the horizontal line test. By the way, sometimes you'll deal with a function like this. Just a straight function y equals x cubed. But if you notice, this function passes, the entire function passes the vertical line test and it would have passed the horizontal line test. So this function, I wouldn't need to limit the domain. The entire function I can find the inverse of. And that type of function is a very special function. We call it a 1, 2, 1. So a 1-to-1 function is a function where that passes the horizontal line test and the vertical line test. We don't have to restrict the domain on 1-to-1 functions. We only have to restrict the domain if it doesn't pass the horizontal line test. Okay. All right, so let's move on a little bit here. So we're going to restrict the domain, and here's what we just talked about here, the inverse function. We had to restrict the domain, and they are missing an equal sign here. I'll make sure that's on your notes. So you have to restrict the domain, so that way the inverse function is also going to be a function too. All right, so how do we figure out how to restrict the domain in order to be able to figure out the inverse function? Well, it's something kind of like this. Let's take this function right here, 2x squared plus 8x minus 1. We're going to go back and do something you did both in integrated 2 and 3. We're going to complete the square. So here's how we complete the square. So first of all, let's write our function. So if I want to restrict the domain, notice this is a parabola. So in order for me to restrict the domain, I need to figure out where this function is going to, where it's going to turn. In other words, if I were to graph this function, it would look like this. So what I'm really looking for is that vertex, because I'm going to restrict the domain at that vertex. So what that vertex at h and k value, when I restrict the domain, I'm going to restrict it so that way the point, hk, that vertex point, that's going to be where it turns over. So I'm going to restrict it at that x value, that h value, so that way it will pass both the vertical line test and the horizontal line test. So anyways, here we go. We were told before, when we want to complete the square, the first thing we have to always do is we have to factor out the a value from the first two terms. So by factoring out the a value from the first two terms, the number, not the x value, just the number that would come out would have been the number 2. So I'm going to factor out the 2, and that's going to leave me with x squared plus 4x and then I'm going to add some number to it to figure out how to get ourselves that value we want. Now realize, if I'm going to add a number in here, and that's the completing the square thing we learned, if I'm going to add a number in here, it's going to change the value of the expression. So if I'm going to add a number in here, then on the outside, I'm going to have to end up subtracting that same number. So, because if I add, say I add 3. Say I add 3. In order to not change the value of the whole expression, I would have to subtract 3, because 3 minus 3 would be 0. So if I'm going to add something, I got to make sure that I also take it away, because I can't change the value of the entire thing. So we're going to complete the square here with this stuff that's in the middle. So we said when we complete the square, that's not quite a square, that's close enough. We put the first term here, and then in order to make this a square, remember that the square has the same length and width. Therefore, the number that goes into these two rectangles have to be the same value. In other words, I have to take this term that I have and I have to split it in half. So that would be plus 2x plus 2x so when I go through and I'm completing my square, I see that I have an x, I have an x, I have a positive 2, and I have a positive 2. So by doing that now, I can figure out what number I need to include here to have to make sure that this is a perfect square trinomial. And in this case, just finish your generic rectangle. So 2 times 2 is 4. So I need this to be a positive 4. So I'm gonna, in order to make this a perfect square trinomial, completing the square, it's a perfect square trinomial, I needed to put a positive 4 here. Now realize the number that goes here is not going to be 4. And the reason why is this value right here isn't just a 4, it's 2 times 4. And this is probably the biggest mistake people make. They'll put a 4 here, but it's not a 4 that goes over here. It's a 2 times 4, or it is number 8. So we added 8, 2 times 4. We added 8 inside, therefore we're going to subtract 8 on the outside. So just so we're aware here, I'm going to add a little arrow to show where we got that. This was the 2 on the outside of the parentheses, and it was the 4 on the inside of the parentheses, and that's where that 8 came from. So now by completing the square, I end up with this function when I change its form. I end up with the function 2 times x plus 2 squared and on the outside I have a minus 9. So in other words, I know what that h and k was. For this particular problem, the h and k would have been -2, -9. So if I wanted to restrict the domain, if I wanted to restrict that domain, I'm only going to be using the portion of it that's going to be x is greater than or equal to -2. Because that's the part I want. So in other words, I'm taking this part right here. I'm taking just that part of the graph. So when I take that part of the graph, it's going to look like this. Well, first of all, let's finish this up here. So that means my domain then, add my little parenthesis, x, I could say less than or equal to too. I mean, that's always okay, but I'm going to use greater than or equal to. So here's what we got so far. We have this graph. We restricted the domain, so we're only going to use just this portion of the graph right here. I lied. I should probably make this more accurate. -2, -9 be down here somewhere. So I'm going to go right about here with it. Okay, so that's the portion I'm going to use. I'm only using a portion of the graph. Now, I'm going to have that line y equals x. That line y equals x. So what they're asking me here to find the inverse function is they want me to do the opposite. So the point -2, 9 on the inverse, x and y would flip because it's reflective of the line y equals x. That would be -9, 2. So they're asking me to actually find, it wasn't quite as curvy as I wanted it to be, but you kind of get the gist of it. They're asking me to figure out what the equation is of that particular function. So again, notice this is the line y equals x. So if I want to determine the equation of an inverse function, I have to take my y and my x, so y is k of x. I have to take my y and my x, and I have to flip them. So this is going to be a two-part thing here. The first thing we do is we flip our y and our x. So I'm going to, instead of this being y, I'm going to make that x. Instead of this being x, I'm going to make this y. And then from there, I'm going to leave the rest of the equation alone. So to figure out the equation of the inverse function, I take my x and y and I flip them. And then I'm going to go through and I'm going to solve for y. So here's my regular function. There's this restricted domain. I'm flipping my x and my y. So that way then I can go ahead and figure out what would be the inverse or the opposite. Remember, think inverse as undo. I'm going to undo every operation and get this new y by itself. So I'm going to take my -9, I'm going to add it to the other side. This says 2 times the whole thing, so I'm going to, instead of multiplying by 2, I'm going to divide by 2. So we're left with this. And then we're going to get rid of our square. So to get rid of a square, we have to take the square root. Now be careful. Usually when we take a square root, there's a plus or minus that goes in front of it. But we're not using a plus and minus here. Notice when I restricted the domain to greater than -2, that was all the numbers to the positive side of it. So I don't need to put plus or minus here like I normally would do. I can just leave it as just the positive value. So I have the square root of x plus 9 all over 2. And then the last thing we do now is we are going to subtract the 2 from both sides. So we end up with the square root of x plus 9 divided by 2 minus 2 equals y. So when I go to write my inverse function, I'm going to use my inverse notation. So instead of k of x for my regular function, for my inverse function, that would be k inverse of x. That says, all right, I'm no longer doing the original function, I'm doing the inverse function. So, and then I would write my equation, x plus 9 minus 2. So I restricted the domain. I first completed the square to figure out my function. I restricted the domain, and then I went ahead and solved it to get the inverse function. Let's have you guys try one. Say, let me give you an equation just for the fun of it. Oh, let's try this. What if I give you the equation h of x equals, let's try negative x squared plus 8x minus 3. Why don't you guys try that one for me? So what I'm looking for here is, what is the inverse function to this function? So I want you to first complete the square to put it in so it only has a single x. And then I want you to restrict the domain. And then once you've restricted the domain, then go ahead and find the inverse function. Why don't you go ahead and pause the video, and you guys can do that now. Let's see. You guys are probably watching me erase this right now. Very entertaining. Need my magic eraser. Speaking of magic erasers, those things are amazing. All right, let's take this, bring it over here. Oh, that's kind of cool. Let's just erase it, actually. We'll draw it back here. Okay, so again, complete the square. We have to first factor out any number out of the first two terms that they have in common. In this case, notice biggest thing we want to factor out is there is a negative here. We really want to get that negative out of there. So let's do that. We have h of x. We're going to take that negative out of it. Let's see here. All right, and again, we're going to add something inside, so therefore on the outside, we are going to do the opposite. We're going to eventually subtract something. So we're going to go ahead and do our generic rectangle here, so we can actually complete the square. So what would be that square that we are going to get here? And again, if you don't actually have to make a square, there is a quicker way to figure it out. Tell you here in a second what that is. Some of you guys already know it, and if you do, that's awesome. And that's a minus 4x. Minus 4x. We take that middle number and we divide it by 2. So we took the middle term and we divide it by 2, and now we'll go ahead and get our dimensions here. X, negative 4, negative 4, and then that. So that's that middle term. So we took the middle number, we divided it by 2 to get negative 4, and then now we're going to multiply negative 4 by itself, so we're going to square it. So that would be a 16 right there. Now this is not going to be a positive 16 that I'm adding to the other side, because remember, there's a negative 1 in front of it. So I have to multiply these together. So I'm going to subtract negative 1 times 16. So I'm going to subtract a negative 16. So I told you there's a shortcut to figuring out these complete the square issue problems. This number right here, it's always going to be the middle term, the middle number. So whatever that middle number is, in this case, it was a positive, or it was a negative 8. You can divide it by 2. That's where we got the negative 4 from. And then you square it. And when we do that, our function that we're actually playing with here. So we have a negative in front of it. We have x minus 4 squared. And then we have a positive 13. So when I'm restricting the domain, I'm going to restrict it at the greater than or equal to the h value. So I'm going to take every x value that is greater than or equal to positive 4. All right, now we're ready to go ahead and do our inverse function. So I'm going to take my y and my x value, and I'm going to flip them. So instead of h of x, I just made that x. Instead of the x here, I'm going to make that y. So we're going to undo everything here. So I'm going to subtract the 13 over. And I'm going to divide by that number in front. So I'm going to divide it by -1. Then I'm going to take the square root of both sides. While I'm at it, I'm also going to just go ahead and divide the -1 since it goes into both. So I get the square root of -x plus 13. And that is y minus 4. And that's the square root of -x plus 13 plus 4 equals y. So that will be our inverse function. So now we write it with our inverse notation like so. Like that. Ta-da! All right. So we can come up with we know how to restrict the domain. We switch x and y and then solve for y to get the inverse equation. And now the last part that we're going to deal with is how do you prove that two functions are inverses of each other? Remember, if two functions are inverses of each other, that means they are reflected over the line y equals x. So if two functions are inverses of each other, they are reflected over the line y equals x. So what our rule here basically says is, all right, if they're inverses of each other, we can prove that they're actually inverses of each other by one way. If we can prove that y equals x. Because remember, say I have some sort of composite function. This right here, this f of g of x, that's really nothing more than just some y. It was just a composite. This g of f of x is some y. That's a composite. So I can prove by using composite functions that y equals x, that y equals x. And if I can prove that y equals x, then I can prove that two functions actually undo each other. So what I'm looking here to do is I'm looking to prove that when I plug the composite of f of g of x and g of f of x, if they both equal x, then they actually are inverses of each other. So in other words, let's start off first of all with f of g of x. Say, take my g of x. I'm going to plug it in for f of x. That means wherever I see an f of x, ever I see an x, I'm not going to leave it as an x. So in my f of x function, this is where x would have been. And I'm going to try to show that when I plug my g of x function into it, they actually undo each other. So that'd be x plus 1 divided by 2. Okay, so now when I go through and I cross off stuff, so I'm looking to see does anything cancel out. when I'm looking to cross stuff off, I can only cross off one thing at a time. So I'm looking at my cubes first. I can cross those off. So my cubes are going to go away. And that would leave me with f of g of x equals 2. So the cubes are gone. If these really are inverses of each other, then they should be able to cancel each other out pretty darn well. The next thing I'd cancel out here, and again, you have to make sure you do the correct order, otherwise we've got to dock you. Turns out then that f of g of x now equals x plus 1 minus 1. And with the ones now, we can go ahead and cross those off, and we end up with f of g of x equals x. So we can look to try to cancel out, excuse me, one thing at a time. And when we do that, we're left with just a single x. Why don't you go ahead and pause the video and see if you guys can do it the other way. Do g of f of x. Go for it. Alrighty, so you guys are back with me now. We're going to try g of f of x. So. All right, so for g of f of x, I'm going to start off with my g of x function. But in place of my x, I'm going to plug in my f of x function. So 2x cubed minus 1. And then I still have, so I took the place of x. I still have the positive 1 here, though. So because it was x plus 1 divided by 2. And we're going to cross off one thing at a time. So the first thing I'd look at here on this time is the 1s. They're going to cancel each other out. Some people say, why can't we just switch x and y and for one of the equations to see if we get the other one? Well, that's how you find it in an inverse equation, but it doesn't prove it. To prove it, you have to go back to the definition of what it means to be an inverse. And again, that means to be reflected over the line y equals x. Okay, so we got rid of our first thing. All right, next part now that we can get rid of are the 2's. So those would go away. That was kind of, there we go. And now we have the cube root of x cubed. And when, like you guys can tell, those would also go away. So we have to prove it for both cases. We have to prove it for f of g of x. We also have to prove it for g of f of x. You can't just do one side. Got to make sure you do it for both. So now, in both cases, look at what I have here. In both cases, I have y equals x. I have y equals x. We were able to prove that y equals x. So the last thing we end up with is we go ahead and we write ourselves a statement. And biggest thing to remember about statements is no pronouns. We don't ever do any pronouns, all right? Since f of g of x equals x and g of f of x equals x, then f of x and g of x are inverses of each other. A lot of people like to say, since they equal x. Well, it's not they. We don't use pronouns. We have to be specific. F of g of x and g of f of x equal x. So we say what we did, and then we say what it means. Then f of x and g of x. And again, a lot of people like to say they again. Then they are inverses. No, got to be specific. Then f of x and g of x are inverses of each other. All right, let's try one more before we call this a day here. What if I give you something just a tad bit uglier? So we need to start off by proving that f of g of x equals x. So f, and we're in place of x, I'm going to plug g of x in there. Equals, so every place on my x, I'm going to plug in my g of x function. So 6x minus 4. This one is just a little bit ugly. When I say a little bit, I mean a lot uglier, actually. And you can't really tell just by looking at it that if they're inverses or not. Sometimes they are, sometimes they're not. So we have to go through and prove it. So we plug in that for our first x, but realize here we have two x's. So that means I need to plug it in for my other x as well. All right, so this is gonna be what we're gonna play with. And this does look ugly. So first of all, I don't like these numbers on the outside of the fraction. So I'm gonna go ahead and put this over 1, and I'm gonna multiply these in to my, I'm gonna make that a -5 right there. And yeah, we'll do that actually. All right, so I'm gonna go ahead and distribute these in here. So in other words, I have f of g of x so I end up with 3 times 6, so that'd be 18x minus 12 all over 5x plus 3. Then I have a 4 over here. And let's see here, I'm going to put this as 6 minus, maybe it doesn't look a whole lot better to you all. So I have a -5. I'm just going to do the 5 right now though. So minus 30x minus 20 all over 5x plus 3. So what I see here now is I see a complex fraction. I see fractions inside of fractions. And friends, I don't like that. Nobody likes that. So I'm going to multiply by that common denominator by every single fraction. So 5x plus 3, I'm going to multiply this over here by it. I'm going to multiply this by it, 5x plus 3. I'm going to multiply every single term by 5x plus 3. Because if I'm multiplying the same thing on the top and the bottom, no matter what it is, say if I multiply the top by 3 and the bottom by 3, what I really multiplied by was 1. If I multiply by x plus 4, by x plus 4, what I really multiplied by was 1. So when I multiply in every term on top and bottom by 5x plus 3, that's really the same thing as multiplying by 1. So I'm not changing the value of the fraction by doing it. What I'm doing here is I'm actually going to make it a little easier on myself because I don't want to play with fractions anymore. I'd like to get rid of them as quickly as humanly possible. And then what ends up happening is this. These common denominators here, they go away. They go away. So I end up with something looking just a little bit nicer. I have 5g of f of g of x equals, these went away, so I'm left with 18x minus 12. And plus, I have that 4 times 5x right here, that'd be 20x. And 4 times 3, that'd be positive 12. So that's what I'm left with in the numerator. What about the denominator? 6 times 5x, that'd be 30x. 6 times 3 is 18. Minus, now remember this whole thing right here, this whole thing was still in parentheses here. So that negative is going to go into it now. So minus 30x. And negative times a negative 20 makes that a positive 20. So let's go ahead and clean up by simplifying the top and bottom here. And we end up with negative 12. So the 12s cancel out. I have 38x on top. The 30x's, they cancel out, and I'm left with 38 on the bottom. So amazingly, 38x over 38, that would be the same thing as, yeah, you guessed it, f of g of x equals x. Well, friends, we did the first one. Guess what that means for you all? You get the next one. So go ahead and pause the video, and you guys try g of f of x. Alrighty, here we go, g of f of x. Let's not kid ourselves. These are just a little bit tougher than the other ones. So let's see here. I got 6 times 3x plus 4. All over 6 minus 5x. So the first thing I always say to do on these, because let's not kid ourselves, they look ugly. They just do. They don't look very pretty. Really just take your time. Oopsies. I got a mistake here. That should have been a minus. Take your time here because it's real easy, just like you saw where I mixed up a minus and a plus. It's real easy to get your signs wrong. Cannot get our signs wrong. So we're plugging our f of x function into all the x's of g of x. And then just like we did before, I'm going to multiply these numbers in. So when I multiply the 6 in there, I end up with 18x. I'm going to leave myself a little space this time. plus 24 all over 6 minus 5x. Then I have a minus 4 there, and then 5 times 3, that'd be 15x, plus 20 all over 6 minus 5x. And plus 3. So common denominators, 6 minus 5x, so everybody is going to get multiplied by 6 minus 5x. I'm going to multiply everything by 1. It's going to multiply by 6 minus 5x. This is going to be multiplied by 6 minus 5x. And this will be multiplied by 6 minus 5x. So getting close to the end here. Hopefully that kind of cleans it up a little bit. And again, we have to prove it both ways because we're trying to prove that y equals x. So these 6 minus 5x here, they get canceled out. These get canceled out. And we're left with 18x plus 24. Minus, now let's go and distribute that negative 4 in there. So minus 24 plus 20x. So that's just taking this negative 4 here and distributing it in. Let's do the bottom now. I got 15x plus 20. And then 3 times 6 is a positive 18. And 3 times negative 5 is a negative 15x. So if we clean up the top and bottom a little bit, hopefully we get some things to cancel, which you can already tell they will. I'm sure you guys already did this on your own. And I am left with 38x on top. And on the bottom, I'm left with, oops, I should have been 15x there. I'm left on the bottom here, I should be left with 38. So again, you see that g of f of x equals x. So now, right here, we have y equals x. We have y equals x. We proved it. All right, pause the video again 1 more second and see if you guys can actually write the correct statement. Remember, make sure you don't have any pronouns. All right, here we go. F of g of x equals x. Got the important word here. Since f of g of x equals x, and g of f of x equals x, then f of x and g of x are inverses of each. There we go. All righty, friends. That takes care of 1.6 inverse functions. Have a great rest of the day.